Today we're going to be talking about Newton's first law and free body diagrams. And Newton's first law can be known as the law of inertia, which basically says an object at rest will remain at rest, and an object in motion will remain in motion at a constant velocity in a straight line unless acted upon by a net force. And so that's a good law to keep in mind. And one of the other things we talked about was this idea of inertia. And inertia basically is an object's resistance to change in velocity, and it is solely mass dependent. So it depends on an object's mass. The more mass of an object, the more inertia it has. The less mass an object has, the less inertia it has. So I have some example problems basically dealing with inertia. Let's take a look-see at them. It says a 5 kilogram cart, or sorry, a 0.5 kilogram cart is rolling at a speed of 0.4 meters per second. If the speed of the cart is doubled, what is the inertia of the cart? Well, remember, speed has nothing to do with the inertia of an object. It's solely based upon the mass, and so this would be unchanged. There would be no change to this cart's inertia. Question 2, which object has the greatest inertia? A falling leaf, a softball, a seated high school student, or a rising helium balloon? Well, I believe a seated high school student would have the most mass, and so thus it would have the most inertia. These other things, well, maybe possible to be really big, and then it could maybe have the same mass as a high school student. Probably won't, right? A ball, a balloon, and a leaf probably will never have the same mass as a high school student. The third question is, again, which has the greatest inertia? And since I know inertia is mass dependent, I'm just basically going to ignore all these speeds at the end of these problems. I'm going to look for which object has the biggest mass. And it sure looks like number 4 has the biggest mass of 20 kilograms, and so that object would have the greatest inertia. So pretty straightforward, I think, in terms of determining who has the most inertia and how it's solely mass dependent. Then we get into something that's a little bit harder. A force is a vector quantity that describes a push or a pull on an object, and forces are measured in newtons. Okay? So this is kind of important here. Forces are measured in newtons, and is named after Sir Isaac Newton. A newton is a base unit. Is not a base unit, but it's a derived unit. The equivalent of a newton is 1 kilogram times meters per second squared. You can break a force down really into two different types of forces. A contact force, in which the object is in direct contact with another object and there's a force being exchanged between the objects, or it could be a field force, where basically it acts at a distance. In first semester physics, the only field force we really deal with is gravity. The rest of them are considered contact forces. Then we come to this term called a net force. And a net force basically is just the vector sum of all the forces acting on an object. So I give an example here. If you and your sister are fighting over the last Christmas gift, and you're pulling on one end of the gift with a force of 5 newtons, and your sister pulls on the other end of the gift with a force of 5 newtons, the forces would cancel each other, and then basically the gift would go nowhere because there's no net force on the gift. So that's what net force basically means. Going on down, I give a nice chart, or at least what I think is a nice chart, of the different types of forces that you might see in class. Again, weight, or the force of gravity, is the only field force, and you can see I label that right here, field force. The rest of them are all contact forces, so keep that in mind. And then I give an explanation of what the force is. I'm not going to read all those explanations to you, but if you are curious, like, well, what's a normal force, or what's the spring force, or the sliding force, or that type of stuff, just read through these explanations, and that'll be, I think, helpful for you in terms of understanding what the force actually is. The third part of this class discussion that I think is probably almost the most important piece is drawing free body diagrams. Free body diagrams are a great way to kind of look at all the forces acting upon an object and then be able to determine what the net force is on an object. The good news is they aren't that hard to do. I basically bring it down to 3 steps right here. First, isolate the object of interest, and then draw the object as a box. Okay, so everything turns into a box, whether it's a person, an animal, a car, whatever, it all turns into a box. Then step 2 is sketch and label all the external forces acting on the object. So a 2-step method to the sketching piece. First, unless the object is in deep space, it's always going to have a weight. Okay, so anything on Earth will have a weight. So first, draw in the weight force on the object. Then second, ask yourself, is anything touching the object? Anything that's touching the object is probably going to be providing some sort of force on the object, and so you'll want to account for that in your free body diagram. And then third is just choose a coordinate system. I typically use right and up as positive, down and left as negative, and that's pretty common in like 99% of physics classes, is that you would use right and up as positive. So let's do some examples of free body diagrams below. So they're asking us to construct a free body diagram for each of these situations. The first situation is a book is at rest on top of a table. Well, the first thing I'm going to do is I'm going to draw a book represented as a box, because everything becomes a box. And I think to myself, well, I think to myself, is the book on Earth? And I think it is. And so it's going to have a force of gravity pointed down. And I label that F sub G. Then I say to myself, what is touching the book? And it would be the table. The table must be balancing out this force of gravity because this book is at rest. There can be no net force on this book if it's at rest. And so the force that balances out is provided by the table, and that is called something called the normal force. And so that's going to balance out this book. Notice I've tried to make, as best I can, these arrows the same length as one another because the length of the arrow is representative of how strong the force is. So you have this book with the force of gravity acting down, normal force acting up. The two forces cancel each other out, so there is no net force on this book. Scenario 2 is a book being pushed to the right across a table with a constant velocity, and it says neglect air resistance. That's what F sub air means. So again, I'm going to draw the book as a box. There it is. And it's being pushed to the right across a table with a constant velocity. So the first thing I'm going to do with this book is I'm going to put in its weight, the force of gravity. Then I'm going to say, well, what is touching the book? Well, the book is on a table again, right? And so the table is going to provide something called the normal force. So it balances out the force of gravity. And since the book is moving on the table is going to provide a frictional force. And I'm going to write that as F sub F, force of friction. Now it says that this book is moving to the right with a constant velocity. So there can be no net force on this book because it has no acceleration. It must have a constant velocity. So to show that, I'm going to draw another arrow about equal length, or as best I can be, equal length to the force of friction. And I'm going to call this F applied because this is the thing, whatever it is, it doesn't really specify, the thing that is pushing the book across the table. It could be a hand, it could be a foot, it could be a chipmunk, we don't really know, but something is pushing this book across the table, and we're going to call that the applied force by this thing, quote unquote. Okay, let's do two more examples together, and then we'll be sitting pretty. It says a book is being pushed to the right across a table surface and accelerating in the direction of the push. So once again, I'm going to draw the book as a box. I'm going to draw in the weight of the book, the force of gravity. It's on a table, and so the table is going to provide the normal force and the force of friction because it's touching the table. Now it says that the book is accelerating across the table in the direction of the push. So the way to show an acceleration is we need a net force. To have a net force, we have to make this arrow be longer. And by making it longer, it's saying that this force is bigger than this force over here on the left-hand side. So I'm going to label that F applied. So whatever it is that's pushing the book across the table is going to be bigger than the force of friction. And so this book is going to progressively get faster second after second after second. Because that is the very definition of an acceleration, is that the velocity is changing. So that'd be the free body diagram of this book in scenario C. Let's take a look at scenario D. Here's a book. Again, it says it's a box this time. A student is pushing lightly upon a large box in an attempt to push it right across the floor, but the box fails to move. Okay, so this box is actually stationary. It's not moving. And the first thing I'm going to do on this box is I'm going to draw in its weight, the force of gravity. This box is on the floor, and so the floor is going to provide two forces. It's going to provide a normal force, and it's going to provide a frictional force. Even though it's not moving, you may say to yourself, well, why is there a frictional force? Well, it's because the student is lightly pushing this box, or trying to push this box, across the floor. So there's an applied force right here from the student. This force of friction must balance out this applied force, or If that didn't happen, the box would actually then begin to move. So I tried my best to make these two arrows equal each other. I probably didn't do a real great job of that, but they're supposed to be equal each other because this box has no net force acting upon it. If there was a net force on this box, it would begin to move and you would have an acceleration because a net force equals an acceleration. That takes care of this class discussion. I'll see you guys next time.